Welcome to online lectures on control systems laboratory. In this video, we will discuss the transfer function of field control DC motor. How to find the transfer function of field control DC motor. Coming to it is a decision motor. Motor is a machine which converts electrical energy into the mechanical energy. So it consists of electrical parameters and also the mechanical parameters. Coming to the electrical parameters, in DC motor, we are having armature winding and field winding. This is a field control method. In case of field control method, we are varying the field circuit and armature circuit is constant. So we are considering only field parameters. Field winding means we are having field winding resistance and field winding reactance. So that we need to calculate. That is the electrical parameters. And coming to the mechanical system. Coming to the mechanical system, it is a rotational system. That is mechanical rotational system, which has the moment of inertia J and dashpot. Coming to the elasticity, it is made up of either cast iron or cast steel. Machine, it is made up of cast iron or cast steel, which doesn't have elasticity property. So no need to consider the spring. In mechanical rotation system, we are taking moment of inertia and friction only. Coming to the electrical parameters, we are having the field winding resistance and field winding reactance. In the same coming to the mechanical system, here we are having only J and B, moment of inertia and friction. Coming to the constants, what are the constants? In mechanical system, torque constant is there. In electrical system, back EMF constant is there. Once if we know these all 6 parameters, then we can write the transfer function. We can identify the transfer function of field control DC motor. Coming to the applications, why you need to identify transfer function, what you are getting from the transfer function. Transfer function is nothing but the mathematical representation of a DC motor. Transfer function is nothing but the mathematical representation of a DC motor. Once if we know the mathematical representation, then we can identify the stability easily. Once if we know the mathematical representation of a DC machine, that is a motor or generator. Once if we know the mathematical representation, we can identify the stability of the system easily. Identify the stability of the system either by using time domain analysis, or frequency domain analysis, or state space analysis. Right. Coming to the apparatus, what are the apparatus we need? 2 rheostats. One is 290 ohm by 2.4 amperes, 14 ohm by 5 amperes. 2 rheostats. Here we have 2 circuits, that is the armature circuit and field circuit. So 290 ohm by 2.4 amperes is the field rheostat, which we are using in field circuit, and 14 ohm by 5 amperes. This one we are using the armature circuit. 2 rheostats, one is connected in the field circuit, one is connected in the armature circuit. And coming to the ammeters, one is used to measure the field current and another one is used to measure the armature current. 2 voltmeters, one is connected across the supply to measure the source voltage, and one is used to measure the voltage across the armature. And tachometer is used to measure the speed, and stopwatch. Coming to the stopwatch, here we need to identify the moment of inertia J. For finding the moment of inertia, we need to cross check the time period to reduce. That means we are running the machine at rated speed and turn off the supply. Its speed comes to the 0. So we need to cross check how much time it is taking. For speed, it is reducing from 1500 RPM to the 0 speed. That 1500 RPM is the rated speed of our machine. So from rated speed to 0, how much time it is taking, that we need to cross check. For that, we need a stopwatch. And coming to the auto transformer, it is a DC machine, but we need to identify the armature resistance, and that is the field winding resistance and the field winding reactance. Resistance means directly you can connect a multimeter across the field winding, you can identify, but coming to the reactance, it's not possible. So we will apply AC supply to the field winding and find the impedance first. Once if we know the impedance and the resistance, then you can identify the reactance. So for applying the AC voltage, for varying the 2-3 voltages, for applying the different AC voltage, we need the auto transformer. This is the apparatus required. Coming to the circuit, if we observe the circuit, is everything same as previous armature control method. Right. Here we are having a DC supply, DPST, double port single throw switch. Fuse is the field rheostat. Field rheostat is connected to the field circuit. Ammeter is to measure the field current, field winding, and return path. This is the field circuit. This is the field circuit, and this is the voltmeter which is connected across the supply to measure the source voltage. And coming to the armature circuit, here the ammeter used to measure the armature current. This is the armature rheostat, and through the armature rheostat we are having armature, and across the voltmeter is there to measure the voltage across the armature. These are the connections. And coming to what your assumptions is that what you are assuming is when you are running at the steady speed, that means the rated speed. When you are running at the rated speed, the power available in the armature, we are giving input. That means electrical energy. Electrical energy is there in armature. That electrical energy we are converting into the mechanical energy. So in armature we are having both electrical and mechanical energy. We are assuming that two are the same. That means coming to the electrical energy, in armature we are having a back EMF constant is there, which is equal to the in mechanical energy torque constant is there. That too we are assuming as the same. Power available in armature, that is electrical and mechanical, both are the same. So the constants also we are assuming as the same. Right? Coming to the transfer function of a field control DC motor, Kt dash by Js plus B into Rf plus S into Lb, where J is the moment of inertia and B is the dashpot and the viscous friction. Rf is the field winding resistance and Lf is the field winding inductance. So we need to identify these all parameters. And coming to the implicit details of DC shunt motor, rated voltage is 220 volts and the rated current is 11.7 amperes. Rated power is 4.2 kilowatts. Rated speed is 1500 rpm. And coming to the procedure. First we are cross-checking the connections, everything. If connections, everything is okay, then we need to cross-check the positions of the rheostats. Coming to the field rheostat. Field rheostat will be always at minimum resistance position. Field rheostat will be always at minimum resistance position. And coming to the armature rheostat, this armature rheostat will be always at maximum resistance position. Armature rheostat will be always at maximum resistance position. Once the positions of rheostats is okay, then we will turn on the supply. And check the speed. We need to run the motor at rated speed. We'll check the speed, and by adjusting the armature rheostat, first we'll try to run the rated speed. If it is not sufficient, and then we'll use the field rheostat to run the machine at the rated speed. Once the machine is running at the rated speed, then we will take the armature current and voltage across the armature. This is a field control method. Armature circuit is constant. So this armature current and voltage across the armature is constant, it won't vary. First we are taking these two values and then we are varying this field rheostat. With respect to speed, we need to cross check. We are varying the field rheostat. So armature current is field current is varying. So this is field current and the speed. These two, field current and speed, we are copying. And we will take 4 or 5 values. We are taking 4 or 5 values. Slowly we will vary the rheostat so the current will change. So based on that current, what is the speed? 4 or 5 values we are taking. Once we are taking the values, we are taking 4 or 5 cases we are checking. Then again we need to run the machine at rated speed for finding the moment of inertia G. We need to check the time taken to reduce the speed from rated speed to 0. So again we run the machine at a rated speed by adjusting the rheostats. Then suddenly we'll turn off the supply. Now machine is running at the rated speed, that is 1500 rpm. Suddenly we'll turn off the supply. Once we turn off the supply means the speed will come into 0. So now we need to cross check how much time it is taking. That is the rated speed to the 0 that we are checking. That is the mechanical time constant that we need to cross check. Once we know, then we'll remove one. We'll see the next how the conduction part will be.
Coming to the conduction part of the field controlled shunt motor. Here this is the circuit. Here we are having the DC supply. DC supply we are giving to the field winding through a rheostat and ammeter. So this is the field rheostat and this ammeter carries the field current. And now we need to measure the source only. For that we are connecting a voltmeter across the supply. And coming to the armature circuit, this is the armature. We are having a rheostat and ammeter. This ammeter reads the armature current, and we need to measure the voltage across the armature also. Okay, first we will give the connections. Okay, we are starting from the supply. Supply is giving to the field rheostat. Here we are having the DC supply. This is the positive polarity. Positive we are giving to the field rheostat starting terminal. And the internal of the field rheostat. Internal of the field rheostat is giving to the ammeter to measure the field current. And the ammeter ending is giving to the field winding Z terminal. And ZZ is connected to the return to the source. Source negative. Right. With this, the field circuit connections is over, and now we will connect the armature part. So coming to the armature part, the incoming is coming from either directly you can take from the supply or you can take from the field rheostat. So now we are taking from the field rheostat. Field rheostat starting terminal. This one we are giving to the armature rheostat starting terminal. End point of the armature rheostat is giving to the ammeter to measure the armature current. And the internal of the armature ammeter, this ammeter measures the armature current. This one we are giving directly to the armature A. And now A is giving to the either directly to the supply or ZZ. You can interconnect directly. And now we need to connect the voltmeters. One voltmeter is used to measure the source voltage, and one is directly connected across the armature. This voltmeter directly connected across the source to measure the source voltage, and this voltmeter is connected across the armature to measure the armature voltage, nothing but the back EMF. So this is the voltmeter. Positive terminal, the return path 250 volts. These two directly are connected to the source. And one more voltmeter. And one more voltmeter, it is connected across the armature. With these connections is over. Now once connections is over, then we need to cross check the procedure. If you observe the procedure, first we are applying the DC supply to the DC motor, and before that we need to cross check what is the positions of field rheostat and the armature rheostat. Field rheostat is always at minimum resistance position, and the armature rheostat will be at maximum resistance position. Right? If you observe, here it is the field rheostat, it is in minimum resistance position, and this is the armature rheostat, it is at maximum resistance position. And now we are applying the DC supply and check the speed. If it is not rated speed, then we will adjust the armature rheostat to get the rated speed. And if it is not possible, and then we will again try the field rheostat to get the rated speed. Once if the rated speed is coming, now is a field control method. So armature circuit is constant. So we are fixing some voltage across the armature and then vary the field rheostat. We will vary the field rheostat with respect to the speed we are cross checking. Right. Now we will turn on the supply. Right now to turn on the supply, and now we need to cross check what is the actual speed now it is running. Now the machine is running at 1090, speed is 1090, but our rated speed is 1500. So now first we are varying the armature rheostat. This is the armature rheostat. Now we are varying the armature rheostat to increase the speed. The speed is increasing. Speed is increasing. So completely varying the armature rheostat, but the still speed is around 1300 only, but our rated speed is 1500. So now we are varying the field rheostat to get the rated speed. So we are varying the field rheostat on the speed 1360. We need to vary from 1500. Once you are getting the rated speed, then first you will check the values. What is the armature voltage we are applying? This is the voltmeter which is connected across the armature. So the voltage across the armature is 103. So we are directly connected to 250, but scale is 125. So into 2 will come. So the armature voltage is 102 into 2.
2 was right. From 252. Okay.
And then coming to the armature current. Now the armature current is 2.1 ampere is there. So here the scale is 5 amperes. You are connected to 5 amperes only. Directly you can take the value. So 2.1 amperes. So the armature current is 2.1 amperes. Right. And we apply the supply voltage is almost 220 is there. And what about the field current now? Now the field current is 0.78 is there. 0.78, approximately 0.78 is there. So we are starting with 0.78. And now the speed is 1500 RPM. Speed is 1500 RPM. Now we are varying the field rheostat. Now we are varying the field rheostat with respect to the speed. You need to cross check. See, now current is the 0.78 is there. Now we are bringing down to the 0.7. Then now the current is 0.7 with respect to the speed. If you observe, speed now we are getting as a 0.7, 1566, right? And next you will increase the speed. You need to increase the speed. That means we are reducing the current value. Previously 0.7 we are placing. Now we are placing at 0.6 amperes. By varying the field rheostat, we are adjusting the field current to the 0.6 amperes. Yeah, now it is 0.6 amperes, and if you enter the speed, we are getting 1636. Now the speed is 1636, and next we are adjusting. Next current we are adjusting to the 0.5 amperes. We are adjusting the current to the 0.5 amperes. So now whatever the speed is, (1697), right? Yeah, once if you know these values, the field current, speed, then you can identify the is a field control characteristics. That means the speed you can convert into the angular velocity, that is the speed omega. That means omega is equal to 2 pi n by 60. Once if you know the speed, then we can identify the omega. Right? And once if you know the field current, armature voltage and the armature current, then you can identify the back EMF EB. Then you can identify the back EMF EB. Once if you know the omega and the back EMF, then you can identify the ratio of EB by omega. EB by omega. And now we will draw the graph between this angular velocity and the EB by omega. It will come like this curve. Yeah, once if we know the field current, speed, angular speed, EB by omega, then you can draw the graph between the field current and this back EMF by omega. From the graph, we can identify this is the graph, like this it will come. Once if we draw the graph from that back EMF constant, KB dash you can find. Once if we know the back EMF constant, from this electrical part is over and coming to the mechanical part, one more we need to find, that is the torque constant. For finding the torque constant, we are using the stopwatch. That means you are suddenly turning off the supply. Now we are running the machine at rated speed and turning off the supply. If you turn off the supply, then how much time it will take that the speed is coming to the zero, from rated speed to the zero, that we need to cross check. So first we will try to run the machine at rated speed and then we will turn off the supply. Now the speed is 1690 is there. Speed is 1690. 41 speed. We are running the machine at the rated speed. Check this. 1536, yeah, 1506, 1478. Our rated speed is 1500, so we are trying to run the machine at the rated speed. So now we are getting the rated speed. Once you are getting the rated speed, now we are turning off the supply. Suddenly we need to cross check the what about the time it will take. The speed rated speed to zero, how much time it is taking. The stopwatch, usually it is at the zero position. Now we are running at the rated speed. Now we are opening the switch and we turn on the stopwatch. Opening the switch. Now the speed is 1393, 1000, 860, 700, 438, 309, 170, 0. So that is almost 21 seconds, right? Time taking to coming to the zero is 21 seconds.
Now, once the conduction of this experiment is over, then you are getting these the values. This is the field current and this is the speed. By varying the field current, we are checking the speed. In field control method, we are varying the field current. Varying the field current based on that, what about the speed we are getting, the copying. Once if we know these two, then we need to calculate the angular speed. Angular speed omega, which is equal to 2 pi n by 60, where n is the speed. So already speed is there. By substituting 2 pi n by 60, then we can convert this speed into the angular speed, that is angular velocity radians per second. That is omega is equal to 2 pi n by 60, where n is the speed. By substituting simply speed, we can convert the speed into the angular velocity, that is the angular speed. Once if we convert it into the angular speed, then we need to identify EB by omega. EB by omega, where EB is the voltage across the armature. Already we calculated. While doing the experiment, we are checking what is the voltage across the armature is there. Voltage across the armature is we are getting 204 volts. Once if we know the EB, and once if we know the angular velocity, angular speed, then you can convert the EB by omega. This EB is 204 and the omega is 157.7. Then you are getting 1.29. Like that you calculate. Like that you can calculate for all the values. By using all the speeds, we are converting into the omega. From all the omega, we are converting into EV by omega ratio we are finding, right? And where this mechanical time constant, tau suffix m is the mechanical time constant, we are getting as 21 seconds, and the armature current is 2.1 amperes, right? This is the tabular curve what we are getting from this experiment. Once if everything is over, then we need to draw a graph. Now we need to draw a graph between field current and ratio of EV by omega. Between these two, we are drawing a graph. This is the field current. This is EV by omega. We are drawing a graph. The slope of the graph. From the slope of the graph, we are finding the back EMF constant, which is also equal to the torque constant. Yeah. This is the graph which we have drawn between the field current versus EV by omega. So the curve will come like this. Curve will come like this. On the slope of this curve, we can identify the back EMF constant, which is also equal to the torque constant. Back EMF constant, which is also equal to the torque constant. Right? The slope of this curve, from this we identify back EMF constant, which is also equal to the torque constant. And if we draw a graph from previous values, previous tabular column, the change in back EMF by angular velocity and the field current, it will come approximately like this. So 0.14 by 0.24. From this we are getting 0.58. This is the back EMF constant, which is equal to the torque constant. Is the value what we are getting from the graph. Now we need to identify the electrical parameters and also the mechanical parameters. Yeah. Coming to the electrical parameters. Coming to the resistance of the field winding. Directly with the help of multimeter we can measure. If it is not there, then we can apply DC voltage by using a rheostat. By varying the rheostat to 3 voltage we are applying, and the current we are measuring. The ratio of that P by I will be the resistance. If multimeter is there, directly we can connect the multimeter across the field winding and measure the resistance. Right? But coming to the inductance part, it is not possible directly. So we are applying AC voltage to the field winding, and first we will check the impedance. Once if we know the impedance and resistance, then we can identify the reactance. From that we can identify the L value. So first we will identify the measurement of impedance ZF. Field winding impedance. For that we are applying the AC supply. To the field winding. So Z is the field winding, motor field winding. We are applying the AC supply through an auto transformer. By varying the auto transformer tapping position, we can apply different voltages across the field winding. So now we need to cross check. We will apply different voltages across the field winding, and we will check what is the current flowing through the field winding. So if we apply 60 volts, what is the current flowing? And if we apply the 70, if we apply the 80, what is the current it is flowing in the field winding? Checking. Once if we know this voltage and the current, from the ZF is equal to VF by IF. So we are identifying the impedance for each and every case, and the average of these three values we are taking as a final impedance. That means the final impedance of the field winding. Average of these three values we are taking as a final field winding impedance. For finding the impedance, we are applying AC voltage. We are applying AC voltage through auto transformer to the field winding, and by varying, we can apply 2-3 voltages, and from that average value we are taking the field impedance. Now once if we know the impedance and the resistance, then we can calculate the field inductance. First we will find the electrical parameters, and then we will discuss the mechanical. So determination of field resistance and the field inductance. Field resistance directly we are measuring with the help of multimeter. And coming to the impedance, we are measuring from the previous circuit, that is second circuit. From the ZF equal to root of RF square plus XF square. Now we know the ZF field impedance and we know the field resistance. By using these two, we are identifying the XF. From that, XF is equal to square root of ZF square minus RF square. So what is the ZF value? 205.4 ohms. 205.4 square. That is the ZF. And coming to the RF, 185. So 185 square we are substituting. And then we are getting as 89.24 ohms. XF value, inductive reactance is 89.24 ohms. Once you know the inductive reactance, then you can identify the LF. That is inductive reactance XF is equal to 2 pi F LF. So from that LF is equal to XF by 2 pi F. From this we are getting as a 0.28 henries. Field winding inductance we are getting as a 0.28 henries. Right? Field winding reactance is 0.28 henries. with this electrical parameters is over, and now we'll see how to find the mechanical parameters. Coming to the mechanical parameters, we need to identify the moment of inertia J and the friction coefficient, that is a dashboard B we need to calculate. So first we are writing the torque balance equations. Torque balance equations for the motor, that is the torque developed, which is equal to J into d omega by dt plus B into omega, torque balance equation. And we are assuming that the motor is running at the steady state. That means the speed is constant. We are running at the rated speed. So the change in speed is 0. So d omega by dt is 0. Change in speed is 0. So d omega by dt is 0. Once d omega by dt is 0, then the first term will be 0. So directly we are having torque developed is equal to d into omega. From the d is equal to Tm by omega, where omega is the angular velocity. That too, here we are running in the steady state, that is the rated speed 1500 rpm. So once if you know the speed, then you can identify the omega 2 pi n by 60, that is 2 pi into 1500 by 60. From that we are getting as a 157.1 radians per second. Right? That is the angular velocity. And coming to the torque developed, we need to identify now torque developed with the DC motor. That means torque equation, torque is directly proportional to phi Ia. It is a field control method. So Ia is constant. Ia is constant. Proportional to infinity, there we are getting a torque constant Kt. So finally, the torque developed, which is equal to Kt into Ia. These two are the constants. So we are taking these two as the constants. So already Kt torque constant we identified from the graph. Previously, we are identifying from the graph. And coming to the Ia, at speed, at rated speed, what is the armature current? Already we measured while doing the experiment. So from this, Kt value is 0.5, which we are getting from the graph. And Ia, it is taken from the experiment while doing the experiment. What is the armature current when the motor is running at the rated speed? That is 2.1 amperes. So product of these two will be the 1.22. 1.2 that we are substituting here, and we are finding B. That we are finding B is the dashboard. We are finding the B. Now, once if we know the B, then we need to calculate the J value, moment of inertia. Already we know the mechanical time constant. We measure the mechanical time constant, which is equal to the J by B. Mechanical time constant, which is equal to J by B. Now we know the mechanical time constant, and we know the B value. From the J is equal to mechanical time constant, that is tau m into B. We already know these two values. Simply if we substitute 21 into 0.078, from that we are getting 1.87. J is moment of inertia is 1.87. Now we know the J value, we know the B, we know the torque constant, we know the electrical parameters RE, RF, and LF also. If we substitute all the values, and that is the final transfer function. That is the transfer function of field control DC motor, which is equal to Kt dash by Js plus T into Rf plus SLF. So already we calculated the J, B, Rf, LF, and Kt dash. Simply we are substituting. Kt is the torque constant. We are finding from the graph 0.58, and J, moment of inertia, we are getting 1.87, and B value is 0.078. And coming to the field resistance 185 ohm, and LF is the field inductance 0.28. This is the mathematical representation of the field control DC motor. This is the transfer function of field control DC motor. Thank you.